Extreme physics.
All right, let's take a look at an ideal pendulum. And an ideal pendulum is a pendulum that has a low mass string, so we can ignore the mass of the string, and at the end it's got a bob, and we can think of this as just a particle. It's a small bob, so we can just treat the bob as a point mass, and the thing swings freely. A massless string and a point mass at the end. That is an ideal pendulum. So let's take a look at analyzing one of these. And so here we go. And here's our pendulum. And here's the vertical. And here's theta. All right, so we're going to take our pendulum and we're going to release it, and we want to analyze what's going on with the pendulum. So this pendulum is in circular motion. So let's analyze that. So we got, I'm going to circle the object of interest, which is the bob, and I'm going to draw a free body diagram. I'm going to use the RTZ coordinate system. The center of the circle is this way. That's my r-axis, like that. And the tangential axis is like that. Here is our object. There's a tension force this way. And the weight is that way, mg. All right. And then if this is our angle right here, is going to be this angle right here, mg. And the motion is going to all be tangentially. So let's take a look at what's happening tangentially. Sum of the forces in the tangential direction equals mass times tangential acceleration. All right, so we only have one tangential force, and that is the component of, it's this component right here. Of our weight vector. So we have negative mg sine of theta is the component that is tangential equals mass times tangential acceleration. But in this case, we're going to say that the tangential acceleration equals d squared s dt squared, right? Where s is this, the arc length. This is going to be swinging down like this, and this is s. This is its path of motion. So the tangential acceleration is the second derivative of the arc length, the change in the arc length. All right, so we can get rid of our masses. And there we go. We got a differential equation. But we're gonna look at something here that's going to help us to solve what would be a complicated differential equation to solve. And in fact, I don't even know if they have a solution to it. We're going to simplify this relationship for under special conditions. And that special condition is going to be a small angle. We're going to use the small angle approximation to solve this situation here. We got a differential equation that's difficult to solve. But for small angles, we do have a simple solution. So let's take a look for a second here. Here I have a unit circle. Here I have the x-axis drawn. And let's take a look at if we had a small angle. So I'm going to draw a small angle. I'm not going to make it too small because I want you to be able to see it. All right, so there I have a relatively small angle theta. And we could see this is the opposite side, and this would be our, I'm going to call this R. And this black section here is S, the arc length. That's the arc length from here to here. And if we're using radians, we have this relationship that S equals R theta, as long as theta is in radians. So we have that, and now we could see if this angle is small, especially if it's even smaller, that S and the opposite side are approximately the same thing. So S is approximately the same as the opposite side in this case, right? And we know that the sine of theta equals opposite over hypotenuse, or in this case, opposite over R, right? Because our hypotenuse is R in this case, is opposite. That's what sine of theta is. But for small angles, opposite over R is, we could swap out S here is approximately S over R. But what is S over R? If we take a look over here, S over R is theta, right? So for small angles, S over R is theta. So for small angles, sine of theta is approximately theta. Sine of theta is approximately theta. We have to be using radians. We have to be measuring in radians. But sine of theta is approximately theta. And this gives, they're very similar for small angles. If you put it, this probably works out to, if we talked about degrees, up to about 10 degrees. Certainly at 5 degrees, it's very accurate. But we do need to use radians when we do these measurements, because this was all based on radians. We're going to use that small angle approximation here to say that the sine of theta is approximately theta. So I'm going to make a statement here. For small theta, sine of theta is approximately theta. So we end up with negative g theta equals d squared s dt squared. All right. Plus we know that theta is s over r, so we're going to end up with minus g s over r equals d squared s dt squared. All right. So we got that. Minus g over r is a constant. S is a variable. So we have a second order differential equation that is clearly a simple harmonic oscillator. This is of the form that I talked about before, where it's minus cx equals d squared x dt squared. Right? Anytime you see something of this form, and that's what this form is, g over r is a constant, s is our variable. So this is a simple harmonic oscillator in terms of s. So now, in the case of pendula, this is usually called L. So we could replace that with minus G over L is our R, right? S equals D squared S dt squared, right? So we know the solution to this function. And we also know that this constant, when we had this, whenever you see of this form, this is a simple harmonic oscillator, and this C equals, it is only a simple harmonic oscillator if C equals omega squared. So in this case, G over L equals omega squared. So G over L equals omega squared. So therefore omega equals the square root of G over L. Or the period equals 2 pi square root of L over G. There you go. There is the period of a pendulum if it is oscillating at small angles. The period equals 2 pi L over G. This is an important result, especially back in the day. Pendula are actually pretty good timekeepers. In fact, it was one of the earliest accurate timepieces were pendula. You had grandfather clocks and cuckoo clocks and things like that. And they would use pendula to accurately keep track of time before we had more sophisticated techniques. So this is, you should be able to easily derive the period of an ideal pendulum. And it's the period equals 2 pi square root of L over G, right? So there's our period. And we could describe S here too. The solution to this equation would be that S of t equals the maximum excursion of S times the cosine of omega t, and omega is the square root of G over L, t plus some phase constant. Right. So there we go. And then we could calculate the speed and all that stuff. So the speed would just be, and the acceleration would be minus a G over L cosine of square root of G over L t plus pi. All right. So there you go. For small angle, this is a small angle approximation. This is only true for small angles. Anything probably less than 10 degrees would be good. If we went way out, we start getting more error. And this pole makes it so I can only do a small angle. But if you did a bigger angle, your results are going to be off a little bit, but they're still going to be reasonably close. But anything less than 10 degrees, and you should get real good results. There you go. You should be able to derive the period of an ideal pendulum. All right, let's take a look at a non-ideal pendulum. This one's kind of big, but it's kind of the easiest thing I have around. Let's see, we got, it doesn't fit very well. Okay, so this is not an ideal pendulum. This is called a physical pendulum, right? And it can also have pendula action. And in fact, a lot of grandfather clocks had a physical pendulum because there would be a massive arm with you'd have a bob that you could slide up and down. But this is a physical pendulum. So what the distinction here is that this has mass distributed throughout, right? So as mass distributed throughout, we don't have our massless string anymore. This is a physical pendulum. It's a chunk of something that's swinging back and forth, right? And it could be any shape or size or anything like that. But it's still, it has a center of mass somewhere down here, and it's going to have a nice pendula action. We're going to assume we're frictionless up there. Let's analyze this. This is called a physical pendulum. Here I'm going to draw a coordinate system like this. And I'm just going to draw this randomly shaped object, whatever it is. It's like that. And it's going to pivot around that point. And here is the center of mass. The center of mass is that point right there. All right. So let's analyze this. So gravity acts as if it all acts on the center of mass. So we got weight pulling this thing down. And here is our position vector relative to the center of mass. And this thing is we've tilted this out an angle theta. All right. So let's take a look. let's take a look at, so this is a body that's rotating, and it has an angular acceleration, all that good stuff. So let's apply the sum of the torques equal I alpha on this thing. Gravity's applying a torque, and this is the torque around the axle. I'll say P. This is some of the torques around P. We assume we have a frictionless axle there, and we got a torque. So I'm going to use the idea of the moment arm here to find the torque. Here's my line of action, and I'm interested in the moment arm, which is the component of the R vector, which is like that, right? So I'm going to call this length to the center of mass. So I'm going to call this R. There's our position vector as it applies to the center of mass. So the moment arm is going to be R sine of theta. R sine of theta. We want this component of R, which is the moment arm, times the sine of theta, right? So that's the moment arm times the weight vector, which is mg, equals moment of inertia times d squared theta dt squared, right? So that's the angular acceleration. So the derivative of the angle is the angular velocity. The second derivative of the angle is the angular acceleration. All right, there we go. We got that like that. So let's get all our constants to one side. R is a constant, mg is a constant, I is a constant, and then we got sine of theta equals d squared theta equals dt squared. All right, so we have a difficult second order differential equation. We got this trig function in it, but as you can imagine, we're going to use a small angle approximation. So we're only going to disturb this by small angles, right? Angles less than 10 degrees, right? We're not going to go way out like this. Oh, see it? Because it tips over. Right? We're not going to do that, right? Just small angles. So for small angles, sine of theta is approximately theta. So we're going to say that this is mg r over I theta equals d squared theta dt squared. Uh-oh, I forgot my negative. That was a negative torque. That's a negative. Forgot my negative. That was negative. Negative. All right. All right, that's a simple harmonic oscillator. This is a constant, and there you go. And this is, of course, omega squared. This is of the form negative cx equals d squared x dt squared. And this is omega squared. You need to know that. You should recognize it. This is called the equation of motion. All right. So this is omega squared. So therefore, omega equals mg r over I square root. And therefore, the period equals 2 pi square root of the moment of inertia divided by mg r. All right? And that's true for small angles. For small angles, that's true. All right. So, why don't you take a moment right now and show that this result collapses to that result for an ideal pendulum. You really needed to only solve for this one, and you could get that one just by taking this and modifying it. Okay, how does an ideal pendulum differ from a physical pendulum? And you see that you should get the same result. Why don't you give that a try right now?
Pause the video now.
An ideal pendulum looks like this. right? All the mass is there. It's at a point. All the mass is at that point. Let's call that R. That length, we'll call that R in this case, just because we had, well, no, we call it L. Let's go with L. You should call it L there. All right. So, well, let's take a look. We had this. I'm going to do this in blue. Let's modify this. So for our ideal pendulum, we have the period equals 2 pi. What's the moment of inertia of an ideal pendulum as rotated about this point? Well, all the mass is here, so the moment of inertia is going to be the mass, which is ml squared. Right? Ml squared is going to be the moment of inertia. All right. There's my moment of inertia. We still got our mass. We got G. And we don't have R now. We call it L. All right. M's go away. Whoa! We got the same answer. I can't believe it. That's amazing. I can't believe that worked. It worked. All right. We got that. All right. Well, it should. This collapses into that. It's the same thing. Right? It better give you the same answer. And that's only true for small angles. All right. So there you go. You need to be able to drive this stuff. It's not complicated. Not complicated. You got to be able to do this. This is the sort of thing you want to be able to do. Let's try a problem. A mass M is attached to a light string of length L, making a simple pendulum. It's displaced a small angle, theta, from the vertical and released at time t equals 0. Directly below the pivot of the pendulum is a stationary second mass M equal to the first, and attached to a spring of spring constant K. On a frictionless horizontal surface, when the first mass collides with the stationary mass, the first mass detaches from the string and sticks to the second mass. At what time will the spring reach its maximum compression?
Pause the video now.
All right, so this isn't too bad, but this really messes a lot of students up. A question like this, because they decide they're gonna set up some oscillator equation, and like this, and they're gonna do something like, okay, I'm gonna do that, and I'm gonna solve for t or something like that, and that's not gonna be a good way to go. It's actually quite simple to figure out at what time does this reach its maximum compression. Because a second later, right after it hits, is like that. This thing was here, and it's going to get squished. Like that. It's going to have the ball attached to it. The string will have broken by this time. And they want to know, how much, if this was the center, they want to know what's the maximum compression of this thing, right? Oh no, actually, what time does it occur? Well, the thing we have to realize is this goes. So we got a pendulum, right? And it goes, pendula. They swing back and forth, and the period is the amount of time that it takes to go from there to there. That is the period, right? Well, in this case, the thing only swung to here. So how much of a period is that? So to go from here to here is quarter period, right? And then this thing is going to hit, right? And an oscillator goes back and forth like this, and this is also going to travel a quarter period. So if we see that, it's an easy problem. If you don't, you're in big trouble. So that's what we do. We got to look at that, and we got to keep our facilities about us. That's why it's important to derive relationships, understand the relationships. They're easier to figure out which one to use if you understand them well enough. If you don't have a good facility with them, you're going to get wrapped around the axle. So the time is going to equal t of the pendulum over 4 plus t of the oscillator over 4. All right. So why don't you give me that? Why don't you take a moment, calculate that?
Pause the video now.
All right. So t of the pendulum is 2 pi square root of L over G, that says capital L, divided by 4, plus our oscillator, right? And that's going to be we got a simple harmonic oscillator, which is a square root of K over M is omega. Therefore, period equals 2 pi square root of M over K. That's the general case. That is just the general relationship. We're not going to use that, though, because our mass is not M, it's 2M. Right? So the T of our oscillator is going to be 2 pi square root of 2M over K, because we have M and another M, divided by 4. Right? So that's going to be our answer right there, which is, I guess, going to be pi over 2 times the square root of capital L, L over G, plus the square root of 2M over K. All right, so there's that's the time. I guess I should label these times here. That would have been smart. 0, 1, 2, 3. So the time from 0 to 3 is that, right? Pi over 2, but I don't think I can simplify that. Yeah, that's about it. All right, so there you go. There is that. If you see it, it's easy. If you don't see it, it's brutal. If you try and put into the, if you try and work this out, this goes very badly. Right? It goes very badly if you do that. So anyways, this is the easy way. It's pretty straightforward if you see it. Let's try the second part. Find the amplitude of the spring oscillations. Why don't you do that?
Pause the video now.
Right, the amplitude of spring oscillations. Oh, why do I have 3? Why do I have 4 points in time? I got 0, 1, 2, and 3. Why did I do that? I gave you a big clue. Because from 0 to 1, we're going to use conservation of energy to figure out how fast that thing's going. Between 1 and 2, we're going to use conservation of momentum. Mechanical energy is not conserved during this collision. This is an inelastic collision. So we're going to use conservation of momentum. And then we got an oscillator at that point. Well, all that energy is going to be, all the energy this had is going to be a spring potential energy at that point. All right, so let's take a look. First, let's figure out how fast. Let's figure out, because we really want kinetic energy at 1. So I got to figure out, again, let's go over here. I'm going to exaggerate my angle. Just to make the drawing easier to interpret. This is going to fall in h, a distance h, like that. And this is L, I think. I guess this is L minus h right here. Between here and here is L minus h. All right. So we end up with, we want to know what h is. But I do know that the cosine of theta equals adjacent, which is L minus h all over L over hypotenuse. L cosine of theta equals L minus h. So h equals L minus L cosine of theta. All right, we're going to need that because we're gonna say that the energy at 0 equals the energy at 1. 1 is right before the collision. So we end up with mgh0 equals 1/2 mv1 squared. Right? I'm going to set the gravitational potential energy equal to 0 at this lowest point. So let's solve this for v. M's go away. So v1 equals the square root of 2gh0 equals the square root of 2gl minus L cosine of theta. All right. So that's the speed at 1. And between 1 and 2, momentum is conserved. P1 equals P2 during our collision. So we end up with mv1 equals 2mv2. mv1 equals 2mv2. So m's go away, and we end up with v2 equals v1 over 2 equals the square root of 2g L1 minus cosine of theta divided by 2. All right, there's v2. That's the speed of these two things. All right, so we have a simple harmonic oscillator. Now, what do we need to realize about this v2? What do we have to realize on that? Now this thing's going to oscillate back and forth like that. What do we know about v2, which occurred at the equilibrium position? Vmax. That is Vmax. Right? That is Vmax. All right. And then we can use conservation of energy again. Energy at 2 equals the energy at 3. So 1/2. I was going to write m, but it's the generic m. This has a mass of 2m. 1/2, that's our mass. 1/2 2m times Vmax squared equals 1/2 K A squared, or Kx squared in this case. Right? That's the maximum excursion. So our x equals A, right? That's our maximum excursion. This thing is going to oscillate between A and negative A, like that. The collision occurred at 0. All right, let's get rid of our 1/2s. And we end up with 2m times 2gl1 minus cosine of theta divided by 2, right? That's our v2. Divided by k equals a squared. Let's get rid of that. And let's go with mgl 1 minus cosine of theta all over k equals a if we take the square root. All right, there's our amplitude. mgl times 1 minus cosine theta divided by k. Square root of that is the amplitude. All right, so there we go. We had an ideal pendulum using that, and we had an oscillator. All kinds of good stuff in that problem. All right, get you there.
Extreme physics.